For this last bit, just going to look at a few that have appeared over, well, a few different years in the HSC to give an idea of what sort of things they'll actually ask us. Here's the random curve. They haven't given us the equation of it. It looks like it's 1 over some quadratic. Is that sort of typical shape of that? But we can't assume that's what it is. Draw separate sketches of. So the first one is the reciprocal graph. Okay, the key things about the reciprocal graph we'll remember. If I turn 2 upside down, well, 2 is bigger than 1. Seeing they've given me a scale, I can sort of identify where 1 is, because that's one of our key points. So 2 is bigger than 1. Turn it upside down, it'll be a half. Oh yes, our vertical asymptotes, when we turn them upside down, they'll become x-intercepts, sort of. Yeah, turn -1 upside down, as I was saying. So turn 2 upside down, we'll get a half. That was a minimum turning point. It's now going to be a maximum turning point. That's pretty much all we need for that one. Well, it's sort of got that U shape of a parabola. My first instinct when I looked at that graph, as I say, is it looked like it was a parabola that was upside down. So when we find the reciprocal of that, it should turn into some sort of U shape. The only difference being is we've got those point discontinuities at the x-intercept rather than actual x-intercepts. Okay. So the next one, function x plus the absolute value of function x. So we're going to get this curve and we're going to add to it the absolute value. So I guess the first thing we need to work out is what does the absolute value look like, so then we can add them together. And the absolute value was anything below, reflect above. So this U part's already above. We're just talking about these 2 little hyperbolic sections will be reflected above. So, right, so we've got the blue curve and we're going to add it to the black curve. Well, what do we know? We know because of symmetry, the bit I've just reflected above will cancel with the bit I've just come from below. So we know that's going to equal 0. And the other part will be twice whatever the original one is. So between these asymptotes, so the minimum point there will go to 4. Between these asymptotes, we'll get some sort of U shape. That answer there is probably the most common incorrect answer. Because what a lot of people did is they said, we'll add these 2 together, but instead of saying, and it will equal 0, they said it will disappear. But it's still there. It's the line y equals 0. So we should also have discontinuity at the x-intercept and then lines going either way. Then they asked us to square the function. Okay, we know stationary points remain as stationary points. So we've got one there, but again, the y value will change. X-intercepts, well, we haven't got any x-intercepts in this one, so we don't have to worry about that. The bit below, when we square it, will go above, because it'll be positive. What are we going to get? So there we go. Our minimum point turns to 4. That again is going to have a U sort of shape. And then when we square it, a bit boring really. The square one. The other ones are much more fun. They have x-intercepts and you get all the turning points and what have you. But there it is. Now this is the sort of one we haven't really looked at yet. So it's what we call composite functions, where you're finding function of a function. And so this is saying draw e to the power of function x. So e to the power of x is the function, but we're substituting in, instead of the x values, we're substituting in the y values of this particular curve. So how I like to draw these ones is just to the side somewhere. I draw the basic curve that we're doing, which is e to the power of x, so I can remind myself what the key features are. And reminding that it's the y values of these will be the x value of the basic curve e to the power of x. So the first thing I notice is the y-intercept. Wherever this curve's y value is 0, it will become 1. Well, this curve never is 0, but we do have a horizontal asymptote at 0. So that tells me my new curve will have a horizontal asymptote of 1. Is that the first thing I put in? Oh no, first thing I did was have a look at the derivative to tell me if that tells me anything about the stationary point. So we know when we differentiate e to the function x, I get f dash x. So the stationary point of the original graph would be when f dash x is equal to 0. So this derivative will also equal 0. So I know the stationary point will still be a stationary point. Again, the y value will change. It'll go to e squared. Let's put that up there. So there's e squared. That will be our stationary point. Okay. So again, in that little section, I'll end up with a U shape again, because then what is happening is I'm going e to the power of bigger and bigger and bigger numbers. And if we look at our exponential graph, as x gets bigger and bigger and bigger, the exponential gets bigger and bigger and bigger. But we have a reflection. Okay. All right, so at this stage, I've circled that because it's a discontinuity. Will it be a vertical asymptote there? Probably not. That's why I've circled it. The reason I know it's not going to be is because, of course, it can never be negative. E to the power of something will always be a positive number. So I can't cut that x-intercept and go asymptotic or something. So I know that's going to be a point discontinuity. And as I mentioned before, I've got that horizontal asymptote now at e to the power of 0, which is, of course, 1. So I've got to go asymptotic. It leaves me with two choices again. Either, okay, so there's one. Either it'll come in very steeply and bend towards the asymptote, or it might inflect. So it might come in shallowly and inflect and go up like that. So there are two options we've got. Again, the derivative could be useful for that, because that's what's the difference between those two curves I just drew in. One's going to have a derivative that approaches 0, that's the one that inflects. One's going to have a derivative that approaches infinity, that's the one that's coming in sharply. So what's our derivative going to do? I've got f dash x times e to the function x. So as we're approaching a value of, now let's get this right, the y value there is 0. So we're saying function x is approaching 0. So we're going to have f dash x e to the power of, what? Sorry, it's infinity, it's not 0, is it? Oh, my mistake. I'm meant to be reading the y values, not the x values off this graph. So it's e to the power of the y values, which is actually minus infinity. So if it's approaching minus infinity, so e to the power of minus infinity would be, so it looks like it's going to be the shallow one. Because remember, the exponential, when you're multiplying functions, the exponential will dominate. So if it's going to be the shallow, it looks like this curve is going to be the one that inflects and goes like that. So, well, a bit bumpy there, but you get the idea of what I'm talking about. Okay, let's have a look at the 2002 one. Here's their random graph. Again, they didn't actually give us an equation of this graph. So I'm just going to guess things like, well, that's a double root there. That's probably a single root there, because it looks like it's cutting through like a straight line. But I can only guess, really. They've told us where -1 is, so they've given us, oh, and +1 over there. So they've given us some sense of a scale. They could turn out to be key points, as we've seen. First one, again, they wanted us to do the reciprocal. This one's a little bit more interesting, because when we turn x-intercepts upside down, we know we get our vertical asymptotes. So let's pop those in. We didn't have any vertical asymptotes in the original one, so I don't have to worry about that. Okay, when I turn -1 upside down, I'll get -1. +1 upside down, I'll get +1. Or possibly there's another -1 over there. Okay. So this one I thought I'd take the shading approach, because I wasn't 100% sure what it's going to do from there. So I thought, okay, let's see, where is it above the curve, where is it below the curve, so I can get a feel for it. So here it's below -1, so turn it upside down, it goes above. Here it's above 1, go below, and so on and so on. So it looks like, in this section on the left, it looks like we've got our classic hyperbolic section again, where we just bend towards those two asymptotes. Looks like we've got a turning point here at 1 minus 1, and it'll bend towards those two asymptotes. And in the last bit, again, it looks like we're going to have a hyperbolic section. So there we go, something like that. Okay. Y squared equals function x. So this is the one where first of all we'll draw the square root graph and then we'll reflect it. Because it's the same as saying plus or minus the square root. So those can be fun until we look at this one and go, oh, how boring. Because you can't find the square root of a negative number. So all the bit that's below, see ya. That's just that. All right. And as I say, it looks like it's a single root. So if it's a straight line like y equals x or something like that coming in, find the square root, that's a parabola on its side. So I'm going to have that vertical tangent and it'll have that parabolic sort of shape, I think. Without knowing the actual equation, I think that's the best I can do. So, but there's the biggest mistake made. That single point there. Because what people did is they said, oh, anything below disappears. But of course there was an x, well, it wasn't an intercept, it just touched 0 at that one point. And of course the square root of 0 is 0, so that single point still exists. And so there's the square root. Trust me, that's vertical right there. It's a bit, yeah. Ooh, who remembers what this one does? Absolute value of function, absolute value x. So we draw a function absolute value x first. Remember, absolute values, they're like grouping symbols, so you always work inside out. So we do function absolute value x. Well, function absolute value x was left-hand side disappears, and then we reflect what's on the right over to the left. And then absolute value of that new curve will be, well, once we've done that, whatever's below will reflect above. So, okay. Oh, that's a little bit dodgy. But there it is. So we've got absolute value, function, absolute value, x. The log of function x. Okay, so let's just draw a log curve over here so I can remind myself of some key points. And that would be 1. All right, so remember, it's the y values of this. We're saying the log of that becomes the x values of my log curve. Now, can't find the log of a negative number. So again, a lot of that disappears. And in this case, we don't have a single point because log of 0 also doesn't exist. So we are just dealing with this small section on the right here. I've put in a vertical asymptote. Might end up being a point discontinuity. Let's just see what happens. But I know it doesn't exist. Again, because the y value there is 0 and we can't do the log of 0. All right, well, the other key point I've got here is 1, and that is also a key point on my log curve. Log of 1 is 0. That will become an x-intercept. From there, what are we doing? Well, it's a log of, and we're starting at numbers that, well, we can't do the log of 0, but as soon as I go past that, it'll be log of a fraction, which is just going to be actually our log curve, isn't it? Because we're going to basically be subbing in all those numbers in there. So we'll just have our log curve going through there. All right. So 8H, have a go at some of those ones.